Welcome, ladies and gentlemen. Good morning. May I have your attention, please? Thank you very much. Let's go ahead and get started. We know we can evaluate logarithms exactly and algebraically using our knowledge of powers. So if we rewrite each of these logarithmic statements as an exponential statement, right, or a power statement, then we'll be able to use our knowledge of powers to figure out the answer. And so let's go ahead and rewrite base to the exponent equals input. For number one, x to the second equals 16. For the second one, base 3 to the second power equals input. For the third one, base 7 to the exponent equals input. And so depending upon where x is, right, you'll use a different strategy for figuring it out. Go ahead and share with the class some answers when I call on you. So number one, if x squared equals 16, then what must x be? Knowing that we're only allowed positive base b's for our logarithms. Aaron? 4. Raise your hand if you had 4 for number one. It's correct. Good. Number two, 3 squared is x, so what would x have to be? Brady? 9. 9. Raise your hand if you had 9 for number two. Awesome, you guys. 7 to the what exponent x equals 49, so what would that have to be? Dakota? 2. 2. Raise your hand if you had 2 for number 3. Awesome, thanks. And so now we'll go ahead and continue on with the party. 2 to the x equals 1/8. The only way to make that 2 into a fraction is if I take its reciprocal. So what kind of exponent causes you to take the reciprocal, Braden?
Negatives would be -3.
Absolutely, thank you. We need a negative exponent to make that 1/2, and then to the third power equals 1/8. Raise your hand if you had -3 for number 4. That's awesome. Good job, you guys. 5 to the first equals x, so 5. Number 6, 7 to the x equals square root of 7. This was on your lesson master, wasn't it? And so this question is really, right, asking what exponent must 7 be raised to so that it equals the square root of 7. And recall, we can rewrite a radical as a rational exponent, a fraction exponent. And so a square root rewritten as an exponent would be to the 1/2 power, right? The 1/2 power. And so 1/2 is number 6, and that was a lesson master question. Number 7, it's useful to think about that decimal input perhaps as a fraction. So that's 1/1000. Therefore, 10 to the what exponent equals 1/1000? Well, it must be reciprocal again, so negative like Braden told us. And then 1, 2, 3 zeros, so I'm thinking -3 if we put it all together. Survey says that's correct, -3. Number 8, x to the 1/2 equals 9, so that's the square root of what equals 9, and so that must be 81, is that right? 81, awesome. Raise your hand if you had 81 for number 8. 81? Good job. And then we need to discuss this last one. X to the 0 equals x, so base x to the 0 exponent equals x, and we're only allowed to have positive bases, but to be a logarithm, we're not technically supposed to have our base be 1, and so the only way to make that work is if we do have 1, but then we wouldn't really be dealing with a logarithm. So that's kind of an interesting question there. The only way to make that work is if the value of x were 1, but typically we don't let our base in our exponential functions or our logarithmic functions be 1. So that's interesting. Number 10 is a great question. 1/9 to the negative 1/2 power equals x. Let's go ahead and write that down. So 1/9 to the negative 1/2 power equals input x. In order to evaluate this, I'd rewrite that as a reciprocal. So 1/9 to the negative 1/2 is the same as 9 to the positive 1/2, and that's just the square root of 9. Oh, so it looked nasty, but it turns out just to be 3. What questions do you guys have on 1 through 10? Then I made a little space for our number 11. Again, anytime you're talking about continuous growth or continuous decay, then you're authorized the use of that formula. A equals P times E to the RT, where E is not a variable, but Euler's number, right? About 2.71828. And so, how much money will you have in an account that is compounded continuously, earning 3.2% interest after 5 years if you invested $780? So here we go. Continuously authorizes the use of our A-PERT formula. Our amount A is given by a principal investment multiplied by the number E raised to the RT, where R is my interest rate as a decimal, just like before, and time T is the term of my loan or investment in years. Let's do it. So we'll go ahead and figure out my amount A. if I originally invest $780 times the number e to the, and then my interest rate as a decimal would be 0.032, right? So 0.032 times, and my time of the investment was 5 years. So let's go ahead and just do a straight home screen evaluation, everybody. Make sure you're comfortable finding that number e. You can find that in two different places. Second ln, that is first column, seventh button. Second ln will automatically spit up an exponent, or you can use the number e second division operation. Second division operation is e, and then you just do a caret for a to the. Let's go ahead and try it. 780 second e to the, I'm going to do the second ln to spit up my exponent already. And up in my exponent, I want 0.032, bless you, times 5. So let's make sure I have that entered correctly. 780 times e to the 0.032 times 5 up in the exponent, and it looks like $915.34 is what I'm getting about. So I'm getting about $915.34. At this time, I ask you to raise your hand if you already had that. So who already had that using the APERD formula? Way to go, you guys. That's great. What questions do you guys have on today's Bellwork? I'm going to go ahead and box this then so we're PDF-able. And we'll go ahead and remind you about your day 4 quiz. And so there's a quiz next class, right? Next class covering 9.1 through 9.4 and 9.7. So the material from 9.7, that is our logarithm discussion from last class, our exponents in disguise, is going to be tested without the use of a calculator. However, you will have your powers half sheet, so it'll look a lot like today's Bellwork, right? It'll look a lot like today's Bellwork. If you'd like additional practice for the non-calculator portion of your quiz, look at day 2 notes, the pop-up shapes. And so those 2 slides that had the pop-up shapes is where we took to do the non-calculator questions. So please go back and find the little triangles and stars and circles. Those pop-up shape pages are basically what your non-calculator portion of the quiz looks like. Does that make sense? Awesome. On the calculator allowed portion, that'll be stuff like the radioactive decay, you know, how much of the substance is present after 200 years, or what's the initial value, right? If 10 grams remain after 29 years or whatever, and so that kind of thing could show up. Or maybe a money question, just like your Bellwork, right? Kind of a money question. Continuously compounding versus compound interest, something like that would be calculator allowed material. Awesome. All right, let's go ahead and give yourself credit for those that you completed on assignment number 2. Everyone, please make sure your name first and last. I'm going to go ahead and pause the recording while we do our homework check, and then resume it when we come back together. Thank you, ladies and gentlemen. Today we're going to evaluate common logarithms and natural logarithms. And so last class we defined and evaluated logarithms of any base b, right, based on our knowledge of powers and exponents. Well, today we're going to take a look at two basic logarithms, right, that share a common base. And so when we talk, that have a base that shows up in real-world applications for the case of natural log, and then a common base 10 that you're used to seeing with our number system for our common log. We're going to solve some logarithmic equations, and we're going to graph logarithmic curves again, kind of like we did last class, to get comfortable with the domain and range and associated properties of their graphs. All right, let's go ahead and get going. So consider the equation x equals 10 to the y. We're going to rewrite that as a logarithmic equation. So while you don't have this on your sheet, go ahead and write in the margin, how would I rewrite x equals 10 to the y? How would I rewrite that as a logarithm, right? What would be my base on the logarithm? So if x equals 10 to the y, then we could rewrite that, and we'd have y equals log base 10 of x, and voila, by golly, it is there. So y equals log base 10 of x. This logarithmic equation gets its own button on the calculator. And so when you see the LOG button on your calculator, that automatically means the base on the logarithm is 10. In fact, from now on, when you see LOG without the base 10, right, then it's implied that that's a common logarithm and the invisible base is 10. So it's called a common log, Logarithms to the base 10 are called common logarithms and are written without a base number. Y equals log of x means y equals log base 10 of x, but we don't write that, kind of to save time. So now we can evaluate three of these, right? Three of these common logs without using a calculator. If my input is a perfect power of 10, then I can evaluate it just by asking an exponent question, right? This is saying, number one is saying the invisible base 10 to what exponent, question mark, equals 100. So, number one, 10 to the what exponent is 100? Well, 10 to the second power. 10 to the second power is 100. The second problem is asking us the invisible base 10 to what exponent equals 1/1000. Right, that's the exponent question for that second one. 10 to the what exponent equals 1/1000. Oh, I know. Right, I need a reciprocal, so that would be 1 over 10. That's a negative exponent, and then 1, 2, 3, 0. So negative third. So I'm thinking that log of 0.001 must equal negative 3. And then number 3, 10 to the what exponent equals 1. Right, 10 to the what exponent equals 1. Barrett? 0, absolutely. So 10 to the 0 power equals 1. All right, as we continue on, is 50, the input on numbers 4 common log, is 50 a perfect power of 10? No. Is 0.25 or 1/4 a perfect power of 10? No, and so on and so forth. So now is when we go ahead and evaluate the calculator. First, I want to check. Everybody, this is important, so we need to figure out how to use the logarithm button. We don't have, right, a button right now for logarithms with base 2 or 7, right, or 6, like on the Bellwork. But this LOG button here is a common log. The invisible base is 10. So for these common log problems, we can check our first 3 answers and then get the answers to the last 3, numbers 4, 5, and 6, simply by evaluating our calculator. Let's go ahead and check the first one and see how we did. Everybody find your common log button. So that's first column. 6th button is common log. Log of 100. Enter. That's 2, right? That's what we figured out already in our exponent question. Log of, everybody do it. Common log of 0.001. Whoa, I've got a lot of zeros there. I don't think that'll make any difference, but we want PDFable. We want PDFable. So let's see. Voila! Negative 3. We got it right. That's good news. Log of 1. Well, regardless of the base on my logarithm, right? If my input is 1, then 0 must be the exponent because any non-zero base raised to the 0 power equals 1. Good. So how do we do? Well, we did very well. Now we don't know what log of 50 is because 50 is not a perfect power of 10. However, we do know what this is asking. This is asking what exponent must 10 be raised to equal 50. So 10 to the first is 10. 10 to the second is 100. And so while I don't know this answer, right, I do know that the exponent must be between what and what? It must be between 1 and 2, right? It must be between 1 and 2. And so I can guess that it's going to be in between 1 and 2. Let's go ahead and see. Everybody, let's do log of 50. By golly, it is between 1 and 2. 1.699 looks like. The log of 0.25 is saying 10 to the what exponent? 10 to the what exponent equals 1/4. In order for that to happen, we must have a negative, right? In order to get to that fraction, we'd have to do a flip, but it's not exact, so there we go. An exact power of 10, I should say. And lastly, log of square root of, oh goodness, 2, close radical, close input. Awesome. And so we'll get our last answers here. It appears as though log of 50 is about 1.699. Log of 0.25 is about negative 0.602. And log of root 2 is about 0.151. Awesome. Okay, so we can evaluate a common log, right, using our knowledge of perfect powers of 10, or if my input's not a perfect power of 10, we can use the common log button on my calculator. So that's pretty sweet. Let's go ahead and get a graph of y equals 10 to the x and compare it with y equals log of x. So then we'll state the domain, the range, the x and y intercept. So for 10 to the x, recall, we can generate, right, points on the graph just like we did in middle school by choosing some x values, plugging into my function rule, evaluating, and then plotting my ordered pairs x comma y, just like we did last class with y equals 2 to the x and y equals 3 to the x. Let's go ahead and do the same thing with y equals 10 to the x. And so consider an xy chart for y equals 10 to the x. And if we chose some x values, right, if we chose some x values, like -2, -1, 0, 1, and 2, we could get the corresponding points on the graph. And so 10 to the -2 would be 1 over 10 squared is 1/100th. 10 to the -1 is 1 over 10 to the first is 1/10. 10 to the 0 is 1. 10 to the first is 10. 10 to the second is 100. So if we consider the graph of our first equation, y equals 10 to the x, in red, it would contain some points, -2, comma 1/100th, -1 1/10th, 0 1, 1/10, and 2 100. So if we connect these, we have y equals 10 to the x. Very steep exponential graph. The domain of my red exponential function is all reals, and so there's no problems. I can plug in any number, positive or negative, into my exponent and evaluate. So the domain is all reals. All real x's. The range, however, is restricted. Notice how only positive outputs are produced. And so the range is only y greater than 0. It's strictly because no matter what I choose my exponent to be, that positive base 10 raised to an exponent will never produce the output 0. So it's strictly greater than 0. The x-intercept? Well, there's no x-intercept. We never reach down to that y-axis. So we get closer and closer the farther we look to the left end of the graph, and that's called a horizontal asymptote. We never get there. So the x-intercept does not exist. Not applicable. The y-intercept, though, for our exponential function is the point 0, 1. And we've seen that in several of our graphs. And go guys around. Lastly, we have a horizontal asymptote at y equals 0. A horizontal asymptote at y equals 0. And that was one of our homework questions on the night 7. All right, let's go ahead and invert the coordinate pairs from my exponential function with base 10 to get my ordered pairs on the logarithmic function with the same base, just like we did last class. The invisible base on this common log is 10, even though we don't write it, it's 10. So it contains the points, right, that are inverted coordinates of the exponential with the same base 10. All right, so what points will be on that? Well, 1 100th, comma, -2. Right here. 1/10, -1. 1, 0. 10, 1. 100, 2. If we were to carefully connect these, points, we'd get our y equals log x graph, our common logarithmic graph. Notice how these graphs are inverses. They're mirror images of one another when reflected off the line y equals x. So we could show that. We could show that if we were to add that invisible line of symmetry, y equals x. The domain of a logarithmic function is restricted, right? Notice how the graph is only produced when I look to the right of the y-axis. In fact, my logarithmic graph only exists for positive inputs. And so my domain is x is strictly greater than 0. Just like the range of my original exponential was y strictly greater than 0. The range, however, is all reals for my blue logarithmic function. So all real y's, is my range for the common log function. The x-intercept, well, we see that as the point, 1, 0. The y-intercept, well, we never get to the y-axis. So just like there was no x-intercept on my exponential function, there's no y-intercept on my logarithmic function. And there's not a horizontal asymptote on this common log function. There is a vertical asymptote, though, and we see that here along the y-axis. So its equation is an x equals equation. That's x equals 0. So the asymptote here is vertical, and its equation is x equals 0. So what questions do you have about our common log graph versus exponential graph with base 10? So we'll see that again. Now let's consider our natural logarithm. And so if we were to rewrite this equation, x equals e to the y, as a logarithmic equation, we could go ahead and write our exponent. Our exponent is equal to a logarithm. The logarithm has the same base that my original exponential has, so log base e of x. Well, if we were to write that, y equals log base e of x, we go ahead and call that a natural logarithm. Remember, e is a number, Euler's number, that shows up in our continuous growth and continuous decay problems. It's about 2.71828. But we don't write log base e. It's so special, it gets its own button on the calculator too. But it's not log log, that's base 10, it's ln for the natural logarithm, a natural logarithm. So logarithms with the base e are called natural logarithms and are written without a base number, and the abbreviation is changed, y equals ln of x. And so we'll be using y equals ln of x to represent a log with the base e. The invisible base on ln is e, okay? The invisible base on a natural logarithm is e. Just like the invisible base on a common log, log is 10. We can evaluate 3 of these again without a calculator by asking an exponent question. So consider the first one on your note sheet, please. What's the invisible base on natural log? Well, the invisible base right here is e, and so this exponent question would be base e to the what exponent equals the input 1. Well, e to what, right? Any non-zero base to what exponent equals 1? Katie? Right? E to the what equals 1? 10 to the what equals 1? No, 10 to the 10th.
10 to 0.
Absolutely, right? 2 to the what equals 1? 0. And so any non-zero base raised to the 0 power equals 1. Absolutely. Good. Thank you. So ln of 1 equals 0. Number 2's exponent question is saying the invisible base e to the what exponent equals e. Well, e to the what exponent equals itself. Adam? 1, right? E to the first power equals itself. Just like 10 to the first equals 10, or 2 to the first equals 2, e to the first power equals e. ln of e cubed, what exponent question is that? It's saying e to the what exponent equals e cubed. What? E to the what equals e to the third? Well, e to the third equals e to the third. You're trying to fake me out? All right. Is 50 a perfect power of e? 2.718? No, nor is 1/4, but it's asking an exponent question. It's saying e to what exponent equals 50, and so we'll be able to reason that out a little bit as well. First, let's go ahead and check with our calculator. We've got a brand new button. So everybody, we've got a brand new button. Everybody, let's find it. The natural log button. The natural log button is first column, right? First column, 7th button. The ln button has the natural log, the invisible base is e. Let's try it out. ln of 1, how do we do? Very well, that equals 0. Natural log of e. Remember, e, the number, is second division operation. So second division operation is where we get just the straight number e without an exponent. Everybody find it. Second division is is Euler's number e. ln of e is 1. Hey, we're doing okay. ln of, and now this time I do want e to the third So ln of e cubed, ready? Yay, math works, we're winning. Okay, so let's go ahead and evaluate the last ones, calculator allowed then. This is asking e to the what exponent equals 50, and so that's like about 2.7, right? To the what exponent equals 50, well 3 is the closest number, the closest integer on our power sheet to e. 3 to the third is 27, right? 3 to the fourth is 81, so maybe around 3 something, 3.9, so 3.9. And lastly, ln of a quarter, or 0.25. Ln of 0.25 is saying e to the what exponent equals a quarter. It looks like negative to get the reciprocal. Good job. So let's go ahead and include those. Ln of 50 is about 3.912, and ln of 0.25 is about negative 1.386. So what are you finding when you evaluate ln of 50, right? What is our calculator telling us? What is that 3.912? So what are we finding when we evaluate ln of 50? Margot?
So like the exponent you need to get 50.
Absolutely, right? The exponent that we need to raise e to get to 50. So 2.718 to the what exponent equals 50, right? That's what we're evaluating. So if I wanted to check, right, and I'm just going to use the decimal approximation right now. I'm just going to use the decimal approximation right now and see 2.71828 to the, because we're just getting about, right, to the, and what did we say that was about 3.912? Right? We said it was about that. So if we did this correctly, if we did this exponent question correctly in our head, this should be about 50. Let's see. 49.99878. So we got pretty close, right? We got pretty close. So that's what it's asking. Good, thank you. All right, let's go ahead and get our common logarithm graph then by inverting points on my exponential function with base e. So once again, ladies and gentlemen, we can generate points on a graph just like we did in middle school by choosing some x values and some y values and evaluating my function rule and plotting those over pairs x comma y on my coordinate plane. So here we go. Let's go ahead and choose some x values like -2, -1, 0, 1, 2, and evaluate my function. Again, I'm going to put them exact, but we'll just plot decimals. So I'll need your help when you change the decimals to get about when we go and make the graph. So y is e to the -2. That's 1 over e squared exactly. Right? That's 1 over e squared exactly. E to the -1 is 1 over e. E to the 0 is 1. E to the first is e, which is about 2.718. And e to the second is e squared, which is about 7.3 or something. All right, so you guys help me out with the decimals. You guys have your calculator? So 1 over e squared, right? 1 over e squared. Is that about 0.15? What's that, Katie?
0.13.
About 0.135. Okay, so we'll go ahead and plot that. Thank you. In red to match the color on the smartboard. So -2 comma 0.135. Great. 1 over e. What's that on my calculator about? 1 over e, Barrett, you got it? Is that about 0.3?
0.367.
0.367, good. So -1 comma 0.367. Thank you, Barrett. And 0 comma 1, I got that. Oh yeah. 1 comma e is about 1 comma 2.7. So here's our 1 comma e. And 2 comma e squared, right? Is e squared about 7.3? What's e squared about 7.3? So 2 comma 7.3. Awesome. Let's go ahead and plot now our y equals e to the x. I'll do it in red. There's our exponential function with base e. Just like our exponential functions we saw last class, y equals 3 to the x, and lastly y equals 2 to the x. And our earlier exponential function today, y equals 10 to the x, the domain and range for my exponential function with base e is exactly the same. What's the domain? All real x's. What's the range? Only positive outputs, and so y is strictly greater than 0. What's the x-intercept? NA. Not applicable. There isn't one. What's the y-intercept? It's the point 0, 1. And again, we've got a horizontal asymptote. That invisible dashed line y equals 0, that the function values approach as you look to the far left end of the graph. And so we've got a horizontal asymptote. Its equation is a y equals equation. All right, guys, let's go ahead and invert the ordered pairs to get the points on my natural log function, y equals ln of x. And so again, the invisible base right here on that ln is e. So its graph is going to contain points that are inverted coordinates from the exponential function with the same base, the base e graph that we just made. So let's go ahead and get some points, you guys. Instead of -2, 1 over e squared, we'll have 1 over e squared, -2. So that was about 0.135, -2. So I'll do that in blue. 0.135, -2. So about here. And 1 over e was about 0.367, Barrett told us. So negative. So we'd have 0.367, -1. 1, 0. E is about 2.7. So 2.718, 1. And e squared was about 7.3, so 7.3, 2. All right, you guys, let's carefully connect those and get our logarithmic function. Again, notice how my y equals e to the x and y equals ln of x are inverses of one another. They're mirror images when reflected about the line y equals x. So I'm going to add that in there just so visually we are reminded of that fact. It'll also help remind some of you on your upcoming tests and quiz from Unit 4. To get points on a log graph, you can make the corresponding exponential function table and then invert the x and y coordinates, just like we did now for the 4th time. The domain of a logarithmic function is restricted. It only accepts positive inputs. And so just like the range of my exponential function was strictly y greater than 0, guess what? The domain for my logarithmic function is x strictly greater than 0. The range, however, is all real y values. And so all real outputs y are produced. The x-intercept, the point 1, 0. The y-intercept, there is none. In fact, x equals 0 is a vertical asymptote. It's like an invisible boundary line, like an electric fence. Right? The function does not exist when x equals 0. So it'll get closer and closer to it, but it'll never touch it. That's a vertical asymptote. So y-intercept, none. And there's a vertical asymptote whose equation is x equals 0. What questions do you have on our common log graph, ln of x? Great. Then you guys are doing very well. We can go ahead and now apply our solving equations from last class in Lesson Master 9.7 in the arena of common logs and natural logs. Let's go ahead and do a couple together. We can solve these equations, right, by rewriting in exponential form. I want you to go ahead and tell the class what the invisible base on a common log is when I call your name. So get ready. What's the invisible base on this common log, this log log? What's the invisible base there? Caitlin? 10, thank you. And so to rewrite this in power form, this is like 10 to the 0.75 equals x. And so we can rewrite that in the corresponding power form. What's the invisible base on a natural log, ln? Get ready and tell the class what I'm calling you. What's the invisible base on an ln, natural log? Margot?
E.
E, good. So as a power statement, this would be base e to the 4th equals x. And number 3, the invisible base on a common log is what? Will? 10, absolutely. So as a power statement, this is base 10 to the exponent 0 equals input n. And lastly, the invisible base on an ln, right? On ln is, Carson?
E to the
Good. E is the invisible base, so e to the first equals a. Now let's go ahead and solve each of these. 10 to the 0.75, right? 10 to the 0.75, I have to do with the calculator. So we'll solve the first one for x. X equals 10 to the 0.75 is exact. I don't know what that is, so I'll get an approximation by doing 10 to the 0.75. And it looks like we, oh no, 10 to the 0.75 lag. Looks like we're getting about 5.623, so that's about 5.623. E to the fourth is exact, right? E to the fourth is exact as an approximation. That would be about second e to the. That's about 54.598. Ten to the zero, we know that exactly, right? What's 10 to the zero? Luke? 1. Thank you. And e to the first is just e, the number e. Awesome. All right, so without using a calculator now, let's use our knowledge of exponentials to state the two integers that the following would fit between. So I don't know, right? I don't know what the log of 75,981 is. But I do know that a logarithm is just an exponent question in disguise. Go ahead and tell the class the invisible base on a common log, an log log. Olivia B? 10. So this exponent question, thank you. And this exponent question is like 10 to the what exponent equals 75,981. Now I don't know that. I don't know that, but I do know that 10 to the first is 10, 10 to the second is 10 squared is 100, 10 cubed is 1,000, 10 to the fourth is 10,000, 10 to the fifth is 100,000, and 75,000 lies in between 10,000 and 100,000. Therefore, my exponent must lie between which integers? Or would that have to be in between? 4 and 5, we think? So between 4 and 5? Let's see. I'm dying to see if we're right. So let's go ahead and do common log. That's right on a calculator. Common log. So common log of 75,981. Survey says, ding, 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 we were correct. So that is between 4 and 5. Nice. And number 2, what's the invisible base on a natural log? Go ahead and tell the class what I'm calling you. What's the invisible base on a natural log? Heather? E, thank you. And so the exponent question for number 2 is e to the what exponent equals 16. Right? And now e is about 2.7, so this is saying 2.7 to the what is 16. Well, 3 is the closest integer on my half sheet, right? That's to e, and so 3 squared is 9. 3 cubed is 27. So we think in between, what? In between 2 and 3? Maybe? In between 2 and 3? All right, let's try. Oh, I want to write down as our guess first. So we're guessing in between 2 and 3. Hey, we have an ln button on our calculator, right? That's why it's useful to work with common and natural logs, so we have those buttons on our calculator. Hey, we were right. 2.772 about. So we're doing okay. Awesome. All right. So we've got a couple more to do together, and then we'll have our closure, right? Remember, we have a quiz next class, and then assignment number 3. So let's go ahead and do some practice. We're going to rewrite the exponential equation as a logarithmic equation and vice versa. Okay, so I want you to go ahead and rewrite this in logarithmic form, right, for each of these, and then go ahead and rewrite in exponential form. Don't be surprised if I ask you to come and share on the whiteboard or share with the whole class. So let's go ahead and rewrite that in logarithmic form. Okay, we'll do the first one together. So I go ahead and rewrite log, common log, I don't need to write the base, of the input equals the exponent. What was the exponent? -3. Go ahead and do the remainder. Too small for you guys?
Yeah.
When you're done with the logarithmic statements, you can go ahead and write the power statements for the bottom three. And you guys are good at that. Base to the exponent equals input. Base to the exponent equals input. Okay, ladies and gentlemen, let's do a quick check. Raise your hand if you had log of 1.197 is about 0.078. Do you have the right placement? Log of n equals m. Who had that right order? Right order? Good job. 10 to the 0 equals 1, we know. 10 to the 2.591 is about 390. You get the placement on that. Raise your hand if you got the placement right on that. And then 10 to the t equals c. Great, we can do the same thing, right? We can do the same thing with solving equations. And so we'll go ahead and write the equivalent exponential equation and then solve. So everybody, let's take a look at 5. What's the indivisible base on a common log log? Mark? 10, thank you. So as a power, this would be 10 to the exponent equals input. And so if 10 cubed equals n, then n must equal 1,000. The indivisible base on my common log, log is 10. So 10 to the -2.86 equals input A. So A must be about 10 to the -2.86. How do we do? About 0.00138. And lastly, we can solve the logarithm equation by first adding and subtracting, multiplying or dividing to get the logarithm alone, and then rewriting in exponential form. So my first step here is not 10 to the, right? My first step is divide both sides by 3. Let's do that, please, ladies and gentlemen. So my best first step would be divide both sides by 3 to isolate the log. Then log of 2x equals 6 divided by 3 is 2. Now we'll go ahead and exponentiate. So this would be indivisible base 10 to the 2 equals 2x. So 100 equals 2x. And x equals 100 divided by 2, both sides 50. You guys getting 50? How could we check? We could take that 50 and plug it into my original right there where I see an x. So if I did 3 log parentheses 2 times 50, close parentheses. If we did this correctly, when I press enter, what should it give us? What should it give us? 6. Cross your fingers, throw salt. We win! 6. Hooray! Alright, I know your sheet is small, but these are just like the earlier common logs, but now with natural logs. So my base E, right, and an exponential corresponds to a logarithmic statement with base E, and we just write ln. So this would be ln of input equals exponent. So ln of 20.086 is about 3. The natural log of 0.223 is about negative 1.5. The natural log of A equals R. And the corresponding exponential formula you guys can do. Some solving and then we'll be close. So on our calculator we can evaluate to the nearest thousandth easily just by using our buttons. But for numbers 6, 7, and 8, right, we would need to do that exactly using our knowledge of powers and exponents. And so for the first ones, it's as easy as evaluating the natural log of 873.5. That's a calculator question. The natural log of 0.0924. That's a calculator question. The natural log of root 2, we can get that. All right. So that's about 6.773. That's about negative 2.38. That's about 0.347. All right, the natural log of E, guys, these are the ones we want to focus on. So these questions ask us to use our knowledge of exponents to evaluate the natural log exactly without using your calculator. So this is an exponent question. It's the visible base E to what exponent equals the input E. So E to the what equals E? Well, E to the first power equals E. E to the what exponent equals E to the fifth? Is that a trick? E to the fifth power equals E to the fifth. Ooh, E to the what exponent equals 1 over E squared. Well, what kind of exponent makes a fraction? Olivia H?
Negative.
A negative exponent, good. So we need the negative exponent to flip it and then raise it to the second power. I'm thinking negative 2. What questions do you have on our exact power statements? Our exact power statements? Okay. Well, let's go ahead and take a look at one application, and then we'll be ready for our code. So suppose the median height for girls aged 2 to 16 is approximated by the function h, with the equation h of a equals 47.28 plus 40.86 times the natural log of a, where h of a is the median height in centimeters of a girl that's a years old. We're going to use this function to approximate the median height of 14-year-old girls. At what age to the nearest month is the median height 1 meter? So we've got a couple different questions here. We're going to use our model to answer these. And so h of a is the median height of a girl aged 8 years, and it's given by centimeters, and it's given by 47.28 plus 40.86 times the natural log of a. Let's approximate the median height of 14-year-old girls. 14-year-old girls. So is 14 going to go in for H or for A, right, according to this model? 14 going for H or for A? Taylor?
A.
A, so number 11A is just an evaluation, and we can go ahead and plug that in for A. Thank you, let's do that. So H of 14 equals 47.28 plus 40.86 times the natural log of A, which is my age, is 14. So we'll go ahead and do a straight evaluation, paying attention to the units in context. So it looks like 47.28 plus 40.86 times the natural log. Remember, we've got a button for that. Everybody find your natural log button, column 1, button 7 of 14, close input. It looks like the median height would be 155 feet. That doesn't seem right. Centimeters? Okay, that seems more reasonable, right? So 155 centimeters. Awesome. And next, at what age to the nearest month is the median height 1 meter? What age is to the nearest month is the median height 1 meter? So this time, what am I going to do? What am I going to do this time? Adam? Absolutely. So we'll rewrite our original model, but this time we're going to put 100 in for H of A. And so Adam recognizes that my 1 meter is equal to 100 centimeters. So we'll rewrite our original model, but we'll put in 100 centimeters in for H of A, the median height. 47.28 plus 40.86 times the natural log of A. I don't know what A is. That's what we're trying to figure out. We're trying to find out that age to the nearest month. So how do I solve a logarithmic equation? Well, remember, we need to add, subtract, multiply, or divide to get that ln alone, and then we can rewrite an exponential form to solve. So ready? That's the first step. Subtract 47.28. Guys, go ahead and help me out with the decimals here. So when I subtract that 47.28, I get, thank you, 52.72 equals 40.86 times natural log of A. And now we're not alone yet. We need to undo this multiplication. So what operation does multiplication? Well, we'll divide both sides by 40.86. Which means that the natural log of A is equal to, what do you guys get for that? All right, so now we're in a situation where we can finally rewrite an exponential form. ln of A, right, the age of the girl to the nearest month is 1.29025. So what are we going to do? Well, we'll rewrite this in exponential form. What's the invisible base on ln? Right, what's the invisible base on ln? Cody? E, thank you. So E to the 1.29025 ... equals input A. That's going to give us our age A. And so it looks like my age A is about, let's go ahead and do that on our calculator. E to the, recall, is second ln, 1.29025, ... Did I do one? Oh, goodness. 1.29? That's good, little bugger. I broke my calculator. overflow. So 1.2905. So we're getting about, does that seem reasonable? About 3.6 years old. Well, when the median age was, when the age was 14, the median height was 155 centimeters. So this makes sense. 100 centimeters is going to be a shorter height, so that must be a younger age. So it looks like about 3.6 years old. So is that about 3 point to the nearest month? So how are we going to do that? Right, how do we get the nearest month then? If it's 3.63. Well, what portion of a year is 0.6333? Well, how far into 12 months is that? Looks like complete July and into August. So now we're in August. Is that right? Seven months completed. And 0.6 of the way through the 8th month, so it looks like August. So to the nearest month, so it looks like 3. Well, we don't have to do, that would just be years, so just 3 years and 8 months. Is that okay? 3 years and 8 months? So about 3 years and 8 months. Awesome. What questions do you have about our logarithmic model? Then let's go ahead and finish up our closure with your partner. Let's go ahead and complete your closure problems, and I'm going to call on you to share with the whole class. Log without a base, written is known as common log. What's the base? ln without a is a natural log. What's the base? And what is it about common logs and natural logs that makes evaluating them easy?
Yeah, I just like to see basic expression logs together.
Okay, go ahead and share with the class when I call on you guys, and we'll get a little bit of work time today. And so common log log has what base? Logan? 10. Raise your hand if you got base 10. Same as Logan, good. Natural log has what base? Marina? E. Raise your hand if you have E for the base on a natural log. E. And then what is it about common logs and natural logs that makes them easier to evaluate? Why do we work with those so often? Luke? Yeah, they get their own buttons on the calculator. So they get their own buttons on the calculator so we can evaluate. Calculator. Right, they get their own buttons. What are those buttons? An LOG button. This is my button, Jackson. Look at that. Ah! And natural log got its own button. I spent a lot of time. Hey, I spent a lot of time drawing that picture. Okay, don't knock it. Don't make fun of it. Look at that. They get their own buttons on the calculator, so we can evaluate our check area. Great job today, you guys. So you can now spend the rest of the time working on your assignment number 3. You may work with another person on pause, and I'll save the recording.